there are really three ways to approach mechanics problems. One is forces and kinematics. That's what we did in the beginning of the class. That's where you're thinking about your position as a function of time, and you're looking at detailed motion. The forces tell you the accelerations, etc. A second way is with energy. That's what we've been working on recently. And here, energy, you have different types, so it's kind of hard to keep up with, kind of a zoo of types of energy. The key is that it is conserved. Energy is conserved for an isolated system or for the universe. And this is good for solving problems where you have sort of initial state, final state situations. Not necessarily the details of the motion during every second, like for forces and kinematics. The third one is the topic of this part of the class. The third one is momentum. That is our new topic, momentum. One advantage, there's only one type. Well, for now. In this class, there's only one type. It's conserved, so we're going to use conservation rules just like with energy. That's good. And it's kind of good for collisions and interactions. Collisions and interactions. Now, to be clear, you could solve any mechanics problem with any one of these three methods, or some combination of these three methods. It's just different methods are sort of lend themselves to different kinds of problems: detailed motion, initial, final, collisions and interactions. So you'll see that as we go. Now, one thing about momentum I want to point out is that it is conserved, but let's get a little more specific, as a vector, because momentum, p, so little p is momentum, it's the vector mass times velocity. So it's sort of a quantity of motion, as Newton would say. Mass times velocity, p equals mv. It is in kilogram meters per second. And that unit has no name. So if you do something really fundamental discovery about momentum, maybe they'll name it after you, because right now it is not named after anyone. Hard to believe. And one thing to keep in mind, it's conserved as a vector. So what that means is that p final minus p initial equals 0. And you'll see why, as we go, why the vector part is important. One reason it's important is it gives you conservation in all three dimensions. It means that px final must equal px initial, and py final equals py initial, and pz final equals pz initial. So that's useful for problems. It gives you three equations. But also there's other sort of more fundamental reasons why it's interesting that it's conserved as a vector while energy is conserved as a scalar, which we'll get to.